Hi everyone. So today I'm going to talk to you about Charmed PostgreSQL, or how to simplify PostgreSQL operation, make them more nimble. We will start by a brief introduction of PostgreSQL. Then we will talk about what it means actually to build a PostgreSQL solution. Then we will present how, let's say, we can operate PostgreSQL the legacy way, the non-optimal way in our point of view. And then we will show you how we think PostgreSQL should be operated, or the better way in our opinion. And then we'll finish with some technical details about our Charmed PostgreSQL solution. Let's start. So PostgreSQL database is quite a mature database. The Postgres project started around 1986, and since then it has been a success. As you can see at your right from Stack Overflow latest survey, PostgreSQL was appointed as the most popular database. And as you can see at your left, throughout DB Engine's popularity index, PostgreSQL has been on the hype for a few years now. And we think it's a deserved hype, because PostgreSQL can actually help you build all sorts of applications, including online transaction processing applications that are common in e-commerce and banking or FinOps sectors. It is as well a pertinent choice to support analytical workloads like what you have with data warehousing and business intelligence application. PostgreSQL is also a pertinent choice if you are managing geospatial or graph data that are, as those capabilities are needed in the logistics and real estate sectors. And this is due to the built-in PostgreSQL capability, but as well to some third-party extensions. So probably the most famous there would be PostGIS and PG routing. And basically an extension is like, a way to extend the capability of PostgreSQL beyond the core functionality of the database. And PostgreSQL can also be a good choice to perform text search and search in general throughout the already quite good capability of the core part of PostgreSQL, but as well using some extension like PG Vector and PG Similarity. And again, those functionality are important for sectors, for example, legal and customer service. So now that we have an overview on PostgreSQL, let's dive into what it means actually, to build a PostgreSQL solution. What are the steps that you need to follow? So the first thing that we need to agree on is that, in order to build PostgreSQL solution, of course, you need to start with the PostgreSQL server, but that's only the beginning. You need to think about high availability. And high availability have two sides: the high availability from the server side, meaning being able to, fill over the service from the primary to one of the replica in case of an issue impacting the primary. But we need as well to think about the client high availability side of things, meaning being able as a client to reconnect to one of the healthy nodes if a problem, did impact the primary server or the server hosting the primary database. Same thing for backup and restore, because backup is often the ultimate and sometimes the only solution to recover from problems like involuntary deletion of data or logical corruption due to software bugs, or even worse, sometimes cyber attacks. We need as well to think about the observability side of things. And observability encompasses a lot of data that you need to collect and to expose and analyze. So metrics, logs, all type of logs, including auditing logs that are, let's say, required in many security framework, like we say DSS, and alerting as well. It's one thing to have the data, and it's another thing to set up alerts so that you can proactively react on issues, or at least even if the problem did happen, at least you react quickly and you try to fix the issue as quickly as you can. And again, depending on your use cases, you would like to extend the core feature of PostgreSQL by using, extensions. And I think we can count more than 1,000 extension PostgreSQL ecosystem these days. Okay, not all of them are useful, for your particular use case, but I can bet you might find, a nice, extension that you can use in your situation. So you need as well to think about security from the get-go. Security is part of all those aspects, and we need to design for security from the start. And we need as well to think about automation, because unless you are managing one or two non-critical PostgreSQL databases, then you need definitely to use automation, because automation will allow you to scale your operation, okay, and will allow you, even if you are using like few databases, only it will allow you as well to have a good reaction time and therefore minimize downtime and accelerate recovery in case of issue. So, PostgreSQL being open source and open ecosystem, that translates into many choices for every, let's say, area that we need to cover in order to have a full PostgreSQL solution. So, for example, for the high availability side, if we are talking about the client, connection pooling and client failover, probably the most popular solution there would be PG Pool and PG Bouncer. And the combination of HAProxy and KeepAliveD are, let's say, a popular solution in order to provide virtual IP capability. In order to manage, like the high availability on the server side, Patroni is another example of popular solution. On the backup and restore front, I think the most popular tools would be, in my opinion, PG Backrest and Barman. And on the observability front, there are a lot of extension to pick, from, and I think the most probably popular one, at least to perform auditing, is, in my opinion, PG Audit. And again, there are a lot of Prometheus exporters that we can choose from. And as we said already, depending on the additional feature that you would like to have, you might be tempted by using some of the popular extensions like PostGIS for managing geospatial data and time scale if you would like to have time-series capability in your database. Yeah. Now let's move to the next step of building a Postgres solution, and it's one of the most important ones because here we are going to qualify the solution as a whole, meaning that we will validate that, for example, the solution behaves as we would like it to behave, in this case from high availability perspective. So in order to do that, we need to run a number of tests, and here we are just, trying to explain some of those tests. So a typical test would be to gracefully or abruptly stop the main database process that we call the postmaster or just Postgres in PostgreSQL database. And we need then to check that either the solution did wait for the main process to be restarted, or the solution did trigger, a failover to one of the replicas. And we should have, in my opinion, a minimum of two instance, so one replica, one primary in PostgreSQL, and we recommend to have 3 or more for better high availability guarantees. And then we need to move down the stack or up, depending on how you see it, and do the same with the cluster manager. So basically the process or set of processes that are managing, the database instance itself. And as I said already, Patroni is one of the famous or popular solution to do, high availability or to manage high availability, not only to monitor the postmaster process, but as well to manage the replication configuration and so on. PG Auto Failover would be another popular choice, and we need basically to simulate failures affecting those processes in order to check that the solution behaves as we expect it to be. We need as well to try to, restart the OS and see if the cluster again or the solution is, behaving as we are expecting to happen. And then we need, if you have, of course, access to the physical infrastructure, we do recommend as well to abruptly reboot the machine in order to check again that the solution behavior matches your expectation. And something that is often overlooked, but we think it's, a mandate to test, is the behavior of your solution, following network failures. And one test that we think that it should be done is to simulate isolation between the primary and the replica, meaning that the primary would not be able to talk to its replica, and check, for example, that we don't end up with a split brain scenario where we have two primary at the same time, because that's a recipe for data loss and data corruption. And actually, in our Charmed Postgres solution, we are running all of those tests and much more on every commit. That's the kind of commitment that you need to do in order to guarantee that your solution continue to behave as per your service level agreements, and that the resulting for example downtime following planned maintenance, like an upgrade or an unplanned failure due to failing hardware, is within your acceptable margins. Now we are going to dive a bit on what it means to operate PostgreSQL the legacy way, or why, how many companies still today, are managing their PostgreSQL fleet, and we will explain why we think this is the non-optimal. So we will try, to script or automate basically the replication setup, a very simple one that involves one primary and one replica, and we will see what that would mean, if we would like to automate it. So in order to do that, we are going to use some nice canonical tools to allow us, to have our testing environment, basically. So we are going to start by LXD, which is a powerful manager for system container and virtual machine. And then we are going to use multipass that helps you basically manage collection of VM. And basically it will allow you to have, as many testing environments or testing recipe as you would like. So after installing both with snap installation, we are going to launch two containers. So one that will, host the primary database that we are going to call here legacy PG1, and one that will host the replica that we call legacy PG2. Of course, we need to connect to the primary database, starting by installing PostgreSQL, and then we are going to just run a dummy query to make sure that the, installation went successfully. Then we need to create some dummy data that we are going to use later on to check that the replication went fine, and that's what we are doing here. Then we are going to configure the wall archival or write-ahead logs, which basically are the changes that are happening in the primary that later on we need to ship to the replica in order to keep it synced with the primary. After that, we need to start configuring, PostgreSQL to allow the replication from the replica and from the replica that we are going to configure later. And for that, we are going to modify mainly pg_fb.conf and postgresql.conf. And that's what we are doing here. We are starting by postgresql.conf, and then we need to, do the same, not do the same, but configure as well pg_fb.conf by allowing the replication stream from the replicate's IP. And that's what we are doing in this, here in this slide. Then we are going to connect to the second instance that will act as a replica, and we start again by installing PostgreSQL. We execute the same dummy query in order to make sure that the installation went fine. Then we take the initial copy of the primary, so basically to make that, the base is the same, and that's what we are doing here. Then we configure the replication, finally, So basically to make sure that all the changes happening from the primary are pulled by the replica, and that's what we are doing here. And finally, we are testing that the replication, setting and configuration went fine. And that's what we are doing by connecting to the primary and issuing this query by selecting some, columns from the PG start replication view. And you should be seeing a line like the following. You can as well test that the replication went fine by, inserting some data in the primary and then checking that, the data was replicated fine in the replica, and we can use the dummy data that we did show you earlier to do exactly that. Yeah, and that was actually only to set up the replication for one node. We didn't talk about automatic failover, we didn't talk about connection pooling, we didn't talk about backup, recovery, monitoring, alerting, and so on. Yeah, and that's why we are calling it a scripting base, because, if you do it, in a naive way, as we were trying to do, and every time you try to add one feature by adding one script and so on, you might end up really by a maze. A maze that will even be more complicated to navigate with, all the parameters that you need to take care about, because only talking about PostgreSQL Server, you have more than 350 parameters to take care of. And you need to add to that all the parameters that will be brought by, all the tools that you might be using, like pgbackRest for the backup, connection pooling, Patroni if you are going to use Patroni for the high availability. And at the end of the day, you will end up by a sensible number of parameters that you should not only understand what they are for and how, you should set up them, but you need to understand, one, how those parameters are, related to each other, and you need to validate, for example, if there is, parameter that is provided by your end user, you need to validate it against the other parameters so that you have, sensible values. You need as well to understand what are the parameters that might be managed by some of your tools that you should not, export, and you should not alter yourself, because that might, lead to unwanted behavior. You need as well to think about the parameter that depends on the environment, like the hardware resources, and try either to, compute sensible defaults, or, like have some auto-tuning, logic, so that, it adapts to the available resources. And on top of that, we need to as well, keep track of the inventory of the servers or VM or containers where we are hosting our databases, and as well the configuration parameter that we are having. Yeah, so that's, another difficulty in managing, Postgres SQL, or let's say a fleet of PostgreSQL this way. So let's move now to what we think is the best case scenario. If you keep, let's say, going this path, you might end up with GitOps approach. And basically, with a GitOps approach, you will have a set of Git repository where you are storing your inventory, your configuration file, and your automation scripts. Okay. And even if there are, advantages to the GitOps approach, but having GitOps only approach will, be challenging in few areas, and here we are naming some of them. For example, how to react to changes quickly, because, typically what you would do with a GitOps approach is that you will feed those, Git repository to a CI/CD pipeline that will try, to apply your changes or your target, state, to your target environment. And that means that you will have, a good amount of delay, when you want to react, to something quickly, like, I don't know, scaling or reacting to a security issue or whatsoever. Yeah. And the other issue that is commonly faced with a GitOps only approach is how to efficiently encode relation between different components in a set of flat files, because that's at the end of the day what you might have there. And for example, in order to express many-to-many relation, you might need to duplicate data, and then you will end up probably with some inconsistency issues, and that's, hard to overcome with the GitOps only approach. That's why we think that there is a much better way of managing, your PostgreSQL database, and that's what we are going to talk about next. So here we are starting by an overview of the components that you are using in our Charmed PostgreSQL solution. And here, what you see is at the DB routing layer that we did opt for PG Bouncer as our solution to perform connection pooling and, client failover. We have at the DB server layer on top of PostgreSQL, we are having Patroni to manage the high availability setup of PostgreSQL, and we are using PG Backrest to perform backup and restores from any S3 compatible storage that are represented here by Ceph. And we have as well a complete observability solution that is based on Prometheus, Grafana, and Loki. And we have as well an alert manager, as we will see later on. So basically, it's a complete solution that is shipped with any PostgreSQL deployment that is supported by our Canonical solution. We have as well Canonical Juju, which is basically a framework of software operator that will allow us to orchestrate all those components and wire them together. And you can think of it basically as our control plane. And our promise, if you are using, let's say, the Canonical solution to operate PostgreSQL, is the following. So you will get up to 10 years of security maintenance for all the used components, not only for the PostgreSQL server, but as well for all the other components that we are using, like PG Bouncer and so on. It will be highly available by default with built-in replication and automatic failover. It will be reliable because it's not only a set of, scripts, it's a state machine-based automation that tries to recover from, issue and self-heal as much as possible. And we did infuse all of our expert and operational knowledge into that, state machine automation. It's, our solution supports automatic upgrades, at your convenience during your maintenance window. And we did, encode our logic to minimize the downtime by minimizing, for example, the number of, primary failover. Our solution is also disaster recovery ready, not only because it has built-in backup and restore capability, but because you can have, for example, in one region, your, main cluster working, and then you can have, in another region using completely different stack, another cluster that is running, that is ready to take over in case of an issue, impacting your primary region. Now that's what we are, let's say, referring to here by hybrid and multi-cloud ready, because, for example, your main region can be using your, Kubernetes private cluster, and then in the other DR region, it can be hosted in one of the public clouds that you did choose to work with. And you can type, in your preferred search engine, Juju supported cloud to see all the clouds that you are supporting, but basically we do support Amazon, Azure, and many others. As I said already, our solution is shipped with a holistic observability stack, as we will see in details later on, that can allow you to monitor basically the fleet of your PostgreSQL deployment. So before giving you a concrete view of how it looks like to operate, PostgreSQL in the Charmed way or the better way, let's, use the same nice tools from Canonical to set up our testing, environment. And here again, we are using multipass, and all what you need is actually 2 threads, 6 gig of free memory, and 24 gig of disk space to basically execute and, follow all these commands, as we right now or at your convenience later on, if you would like to try this in your laptop. So first, we are going to install MicroK8, which is Canonical's pure upstream and highly variable Kubernetes, and it will act as the backing cloud. As I said, Juju support a set of clouds, and K-test is one of them. And then after, enabling few add-ons, when you type MicroK8 status, --wait -ready, you should see an output similar to the following, where you see at the top that MicroK8 is successfully running, and then the list of add-ons that we did enable, yeah? Then we start, basically by installing the first component of our solution, which is Juju, the control plane, and then we are going to tell Juju, to use MicroK8 by typing Juju bootstrap MicroK8 and then giving it a name, micro in this case. And as I said, it's basically telling Juju that you will be using this cloud because Juju is able to use, many more clouds. And then you will type Juju add model PG demo. You can think of a model as a namespace. Basically, you are going to host, our databases here in this demo. And it's actually a best practice to isolate, the database in their own namespace. And that's what we are doing here. Then, we are going to deploy our first PostgreSQL instance, and it's as simple as typing Juju deploy, the name of the operator that we are going to use, so PostgreSQL, -K-test in this case, and then we are going to specify the channel, yeah. And then just after a few minutes, depending, of course, on your network bandwidth and hardware resources, you should see something like the following, yeah. And as we said, running one instance is not recommended for high availability, and we do recommend to run a minimum of 2 or even better 3 instances, and that's what we are going to do again with the simple command Juju scale application, the name of the operator, and then the number of units or instances that you would like to have. And again, just after a few minutes, you should see, something that resembles the following output. And as we said, it's not only about PostgreSQL Server. Our solution supports, much more. And here we are trying to deploy PG Bouncer, so the proxy, database proxy layer. And we are specifying at deployment time the number of units that you would like to have so that we can do it in one shot, not, deploy and then scale. And that's done by specifying the parameter and, -n2. And again, after a few minutes, typing Juju status should yield, the following result, yeah? And you can see here that Juju is helping us by telling us that, we deployed the proxy, but we cannot use it before relating it somehow to the PostgreSQL server. And this is where I think one of Juju's superpowers comes into play, which is the integration concept. So basically, all what we need to do is to type Juju integrate, PG Bouncer, Postgres. So basically, we are linking the proxy to the database server, and just after, a few seconds, typing Juju status should show an output similar to the following, and you can know that the message disappeared. It might look magical at first, but it's not. And I think it's one of the strong idea of Juju that we need to understand. And that's what we are going to try to do together here. So typing Juju status, dash integration should yield, a result where you can see the following at the bottom of it. So you have this kind of table where you have the integration provider in the first column, the require in the second one, and then interface and type. And basically the way to think of it is that the integration provider lists, the endpoint or service provider, and then the requirer is basically listing the consumer of those services. So for example, if we, look at the third line from the top, we can see that PostgreSQL KTest is providing a service or endpoint service that we are calling database, and the consumer of it can be pgbouncer KTest backend database. And basically, that's what is happening when we are typing Juju integrate to application. Behind the scene, Juju is creating a relation between the two service endpoint that will allow the two sides, basically the integration provider and the integration requirer or consumer, to exchange information to establish a communication link between both. And all of this is basically encoded, in the operator themselves. You don't need to do any manual intervention yourself, and that's really why I call this Juju superpower. And in order to validate that all of this is running fine, it's not just to show off, we are going to use a dummy application that we call data integrator. Actually, it's not only dummy application because it can allow us to manage credentials and to generate for example password username that you can use from outside Juju in order to integrate applications that are not yet integrated in the Juju ecosystem. And we start again by deploying data integrator. We integrate it to pgbouncer so that it talks to pgbouncer, and pgbouncer will forward all the requests to the database. And the first thing that we are doing using run data integrator leader get credential is basically we are telling the data integrator to generate credentials that we can use in order to connect to the database. And that's what we are going to use in order to connect to the database using pgbouncer as proxy layer. So we are starting by installing PSQL, which is like the famous utility to connect to PostgreSQL. We are providing as a host the pgbouncer IP, as a username, the username that we did get before, and the password, the one that was supplied by the previous command on the data integrator. And if everything went successfully, we should be able to issue this command that is selecting from pgstat activity and pgstat SSL a number of information. And we are taking basically the opportunity of this query in order to check the state of SSL in the database, and we can see that it's not activated right now, so it's set to false. And of course, we recommend to secure your connection, your communication on the wire, and that's what we are going to do just after, again, with another operator in a matter of few steps. So we start first, I think now you know how it goes. We start by deploying the TLS certificate operator. We configure the TLS certificate operator to make it, tolerate self-signed certificate. Of course, this is only for demo purpose and production environment. We advise against that. And then we just need to integrate it. So integrate the TLS certificate operator to PostgreSQL and then to pgbouncer. And that's what it takes to activate, encryption on the wire for your communication with the database. And in order to prove that, this time we are going to use this kubectl command in order to connect to the container where the PostgreSQL server is running. And we are going to use PSQL that should be already part of the image to the PostgreSQL server. So not going, throughout the proxy, even if we could have as well, connected throughout the proxy as we did before. And using the same username and password that were supplied before, we can issue the same query. And now we can see that the SSL column is set to true, which means that, the encryption is activated. Now we are going to talk observability. And before, showing you how we are going to do that, we need to enable one more add-on for microcaches that is, MetalLB, and that can be simply done by the following two commands. Then we are going to create a new namespace or a model by, typing Juju add model cost. That's the name of the namespace that we are going to create, that it will host the observability stack. we are going to switch to this namespace using Juju switch cost, and then all what it takes is to type Juju deploy again coslide, the name of the bundle that contains all the components that are needed to perform observability. And just again, after a few minutes, you should see, an output similar to the following. And we can, basically identify a few components there. So Grafana, Loki, and Prometheus, and the alert managers again, and Traffic, which is a reverse proxy that we are going to use to expose some of the services that we have in the observability stack to the outside world. Then here, an important, concept is after, deploying the observability stack, we are going to tell Juju to expose some of the services that are exposed by the stack to outside of the namespace or the model. And that's what Juju offer is doing basically, yeah? So once we type those Juju offer commands, we can type Juju switch pgdemo to switch to the namespace where we have the PostgreSQL server, and type Juju find offers to make sure that, the services that are exposed by the cost or the observability stack are now, let's say, readable or reachable from the pgdemo namespace. And now we are going to wire everything together by deploying the Grafana agent that basically is going to collect, all the logs that we need to send to the observability stack, and that's what we are doing. So we start by deploying the operator of Grafana agent KTest, then we integrate Grafana agent, to the cost or the observability stack part, and then we integrate it with the PostgreSQL server part. Then if everything, went fine, typing Juju status integration would yield the result like the following. So you see basically this is where PostgreSQL server is running. We find as well PG bouncer, we find the Grafana agent, the data integrator, the TLS certificate operator. And then you see all the integration point that we did perform, yeah. And in order to check that this worked fine, we are going to switch back to the namespace where the observability stack was deployed. So that's what Juju switch cost is for. And then we are going to, use Traffic in order to expose, the endpoint that we are going to use in order to connect to the Grafana dashboard in our case. And you can see that the next comment, Juju show unit catalog, will show us the URL to use in order to connect to Grafana. And that's what we suggest you to do using your preferred browser. And doing that should, connecting to that URL should, show, the following UI, where we have welcome to Grafana, and then as a username, you can type admin as the default username. And in order to get the password that you can use, you need to run the command that is, commented here in green at the bottom. Juju run Grafana, get admin password, dash model cost, and you can use that password to connect to Grafana, and you should be able to see, one of those, dashboards that are pre-built in. And here I took the example of, a database where we have some traffic so that the graph looks nice, but you can see here that we have a number of information regarding memory, CPU, shared buffers, active sessions, and transaction, and so on. So we have really a lot of information that we are exposing that we think are very valuable for you and your teams to manage your databases, yeah. And we will finish, this part by testing the high availability part of our deployment, because again, high availability is not only about having many replicas. Okay, we need to make sure that if a problem happens on the primary, an automatic failover did happen. That's what we are going to test right now. So we start by typing Juju status in order to identify the PostgreSQL instance that have the primary role, and in our case it's PostgreSQL KTest, /0, and then we are going to identify the pod that corresponds, to this primary PostgreSQL instance, and this is done by using kubectl get pods and then supplying the name of the namespace, so npg demo, and we can clearly see that there is a PostgreSQL KTest /0 that corresponds to the primary, yeah. And in order to simulate a failure affecting the primary, we are going to use the kubectl delete dash now command, and this basically stop abruptly the PostgreSQL the pod containing the PostgreSQL primary. And just after a few seconds, typing Juju status should show you that the primary role was moved to one of the other healthy nodes. In our case, is PostgreSQL ktest, /1. It could have been the other one. And basically the previous primary was, is in maintenance mode. And because, PostgreSQL ktest pods are part of a stateful set, Kubernetes working the way it works, it will try, to scale it up again. And actually, after some minutes, you will see that PostgreSQL ktest 0 is up again, and now it did join back the cluster, as a replica. So that's, was a quick demo of some of the features that are offered by, our PostgreSQL operator, what we call the Charmed, Postgres. And we will now move to explaining some of the technical details, behind, our deployment. And we are going to suggest you to run those commands, those kubectl commands, so to get an idea about the namespace that were created, the pods that are, part of the control namespace, because, what we call the control plane. So Juju is actually, deployed in its own namespace, and that's basically what we call the control namespace. And then we are going to inspect the pods that are part of that namespace. And we can notably, see the API server that basically is receiving the Juju CLI command that we did tape, and will, communicate them to the other charms and to the other namespace if needed. We have a database where we are storing all the configuration that we need and all the objects that are basically part of the, Juju deployment. And we can do the same actually in the other namespace. So in this case, we did choose to do the same for the PG demo, where the PostgreSQL, database and the other components are deployed, and we can identify the following pods. So we have two pods that represent, the PG bouncers proxy, and we can see, that are part of the stateful set. In that stateful set, we have two pods, and in every pod, we always have, the workload container, so PG bouncer itself, and then the operator container, where we have the logic that manages PG bouncer. And similarly, on the PostgreSQL server side of things, we have again a stateful set. We have 3 pods because we did choose to deploy 3 units. We have again each time, the container hosting the workload itself and the container hosting the operator logic itself. And within the workload container, we, in addition to PostgreSQL, as we said, we are using Patroni, we are using PG Backrest. You will find them as well there. We did as well create automatically 2 Kubernetes services. So one for read-write traffic. So basically, it will be used to talk to the primary, and read-only service that can be used to scale your reads basically on the replica. And basically, what we are trying to say here is that it might look magic at first, but it's not. I don't believe there is such thing as magic. But we are, let's say, doing what we are doing by using a list of curated components or a curated list of components that we are validating, as a whole solution, as a whole, not like, separately. And we are, let's say, embedding some of the best practices in the code itself, not just as a best practice written in a document, but we are enforcing those best practices like isolation between, containers, putting in the same pod the operator and its workload, creating, the different service for read-write traffic and read-only traffic within the code itself. And it's enforced by Juju as our framework for software operator, and they are as well enforced by the operator logic themselves. So that's basically was our, quick talk about PostgreSQL. Thank you all for your time. Have a good day, everyone.
Today, I'm very excited to be here to talk about Charmed Spark, which is a new product that we actually just launched in mid-October, and really aims at basically allowing you to bring your Spark workload to Kubernetes. In really, the main goal is to actually provide an extremely seamless experience to do so. So during the talk, just feel free to actually drop any question in the Q&A section, and such that you can also get some answer. So, but let me first start with, what is Spark? So Spark is actually a data processing framework that really enables data scientists and data engineers to basically really scale either their analysis, their processes, or more in general, their application to really massive data sets. And it does that by really distributing the data processing task across multiple computers, and therefore being an extremely interesting and cool tool for really enabling big data processing and as well as machine learning. And as you can see from the trending line, since its inception around 10 years ago, Apache Spark really gained a lot of momentum. And this is really because, well, first of all, it was really operating on an extremely hot topic, hot sector, which is about big data and machine learning, but also because it was actually able to outperform existing technologies such as Apache Hadoop, and really becoming the standard de facto when it comes to big data processing. And nowadays, it's an extremely well-established project that really features a number of integrations with very many other data platform products, such as Elasticsearch, Kafka, Redis, MongoDB, and so on. But how can Spark achieve this scaling out to massive data sets? So from a very high perspective, a Spark application is composed of a driver program. And a driver program can be, even as simple as a Python script. And actually, indeed, from a developer perspective, Spark can just be seen as a replacement for some very common Python libraries, since it really provides similar capabilities, for instance, to process structured data as much as pandas. However, whereas when you use this Python library, such as pandas, the processing happens locally. So in the end, you're really bounded by the amount of memory that you have in your local machine. Spark, what it does under the hood, it actually talks to a cluster manager to allocate resources, which are called executor, on a cluster. And that's in the executor that data is cached and where data processing is happening. Therefore, basically creating like an architecture where that can really scale out to really massive data set that can really parallelize. Now, over the years, Spark really supported a number of cluster managers, but it's really in 2018 that an extremely interesting development came along with the integration as a cluster manager of Kubernetes. And we see that this is very exciting because this integration really powers Spark with the native capabilities of Kubernetes, of scaling out and being extremely flexible, as well as it also provides a consistent user experience across different environments. Because, for instance, you can really run Spark locally against a deployment of micro. Or you can also run it against a Charmed Kubernetes, which is deployed on a bare metal cluster. Or you can even use cloud resources such as EKS. Really, therefore, we're really providing a consistent UX across all environments. But of course, this brings a little bit more complexity to data scientists and data engineers, because to operate Spark on Kubernetes, they have to understand to some extent the internals, the mechanics, the specifics of Kubernetes. And that's exactly what Charmed Spark addresses, which is this product that we just launched in mid-October. So Charmed Spark aims at providing a user experience of running Spark on Kubernetes, which is as seamless as possible. And it does that by really leveraging on the standard Canonical tooling, since Charmed Spark actually bundles together different artifacts. So we provide within the Charmed Spark solution a rock image, so an OCI image with the Spark binaries and some extra capabilities on top of it. Then we also provide, as part of this solution, a snap, the Spark Client Snap, which is basically a package that you can install in your local machine or in your edge nodes, really to simplify the interaction with a Kubernetes cluster where you want to run your Spark workload. And last but not least, we also provide a set of charms that really allow you to enable monitoring capabilities on top of your Spark jobs. And so in this observability bundle, we actually package different services, as you will see like in a minute, actually targeting both user like data scientists and data engineers, to allow them to drill down the logs of their Spark jobs, but also some Grafana dashboard that allows cluster administrators to actually monitor the resource consumption on the cluster. And of course, all these applications, they are deployed and managed using Juju. And as you can see in this picture, really like these three different components, the snap, the rock, as well as the charm, they really play one with another to really create an end-to-end experience. So for instance, as a user, you would use the Spark client to set up your Kubernetes cluster. Then you would still use the Spark client also to execute your Spark application. So spawning a driver as well as the executor that they are based on the Charmed Spark image on your Kubernetes cluster. Moreover, still with the Spark client snap, you can also configure your Spark application to read and write from an object storage. And possibly even more importantly, you can really simply configure these Spark jobs to actually integrate with the observability bundle that we provide. Observability bundle that, as we said, it's deployed and managed by Juju, and it's really composed, as you will see, by different components. So within this bundle, we provide, for instance, a history server. And the history server is basically this component in the Spark ecosystem, which is able to read logs from S3 and aggregate these logs and expose these logs to the user, to a data scientist, to the data engineer, to really drill down using like a graphical interface, the logs for the Spark application. Also, we provide like a Prometheus push gateway that basically collects the metrics from driver and executor, exposing these metrics to Grafana that basically does the dashboarding and expose this information to a cluster administrator that can also set up some alerting system. And once again, all these, the integration of all these components, you see here, you have only 4, but in reality, as we will see, there are way more many components in the bundle. They really, Juju actually allow to integrate them seamlessly in an extremely nice user experience. So we are going to actually show how this works. So there is a GitHub repo that you can refer to, where there is really all the instruction to actually set up the demo that we are going to see today. So today we are really going to use Charmed Spark to set up a end-to-end process, pretty much the picture that we've seen before. So we will be first setting up a Kubernetes cluster, then doing a simple development. And, the first 2 steps will be done locally using microcase. But then once that we have done the development, then we will scale this out using Amazon EKS. And that's when you scale out things, when you start to operate the platform, to operate Spark, that really Juju will be a key player, and everything will be powered, as we have seen, by Juju. So let's start from the setup. So first of all, we will use the Spark client to set up the Kubernetes cluster, as well as an object storage. We will use Amazon S3. So since we are going to use Amazon S3, we recommend to export some environmental variables, which are basically like the credential for the S3 buckets. So after exporting this environmental variable, you can just install the key components of this demo. So microcase, the Juju CLI, and of course the Spark client snap. I have already installed these components in this local machine. So you see that if I fetch microcase Juju Spark client, I already have them running. More importantly, I already have a microcase cluster running. So you see that the cluster is indeed running. And we have a number of add-ons which correspond to what you see also like in the README. Next thing that we are going to do is also to set up the S3 buckets. So as we have said, we are going to bind our Spark workload to these S3 buckets. So we provide actually in the repository an extremely simple Python script that really allows you to set up the bucket really in no time. So if now we go to the S3 console, you see that here we have a new bucket, which is operator day 2023 Charmed Spark. And we have 3 folders. And we have, for instance, a data folder where we have already uploaded some data that we we're going to use in this step. All right, next thing that we are going to do is actually to set up, to configure the Kubernetes cluster to run Spark jobs. And in order to do this, we have to basically create a Spark service account. So with the Spark client snap, we actually provide some functionality to create and to set up a Spark service account with just one command. And moreover, you can actually configure this Spark, this service account with some information to allow the Spark jobs to actually bind to S3. So as you see, we have like a file, a configuration file, and we can use the Spark account register, the service account registry to create this the service account. So you see that now we indeed have in kubectl in Kube a Spark account, and we also have created some secrets. The secrets where basically all the configuration will be stored. Okay, so that's it. Now we are indeed ready to use Spark on Kubernetes. So the next thing that we said we are going to do is actually to start off a Spark application. So actually this is also a good opportunity to also stress another functionality that we provide. In fact, many data scientists and data engineers, they are quite accustomed to using the Jupyter Notebook. So within our image, we actually provide a way to run a Jupyter Lab using Docker. So, but that's an enhanced version of Jupyter Lab, since it's a version that whenever a notebook will be started, it will be treated as a driver. So the notebook will be the driver. And as you have seen in the Docker container, we have also mounted the kubeconfig file. So we have a binding to Kubernetes. So whenever we are going to start a notebook, effectively, we're going to indeed to actually also start some executors. So the notebook will be our driver, whereas in the Kubernetes cluster, we will have the executor. And in fact, you see now that we have started, as we started the notebook, we also started some pods on microbit. As a side effect of this, in the notebook, we also injected some variables. So for instance, this SC that you see in the Jupyter Notebook, which represents the binding to Spark. So as you can see, now we have indeed a binding, Spark context already available in the notebook. And we can, in the notebook, start to read some data. But be careful, because in this case, the data is not going to be placed in the notebook, but they are going to be read in the executor, where the actual processing will happen. So basically, this information, this instruction will just trigger this reading, and will also infer the schema of the data. So we are already doing some processing on top of the data to infer the schema. And indeed, once the reading and the infer is done, we can print out the schema, and you see we are going to deal with sales data. So we have an invoice number, we have a stock code, quantity, price, and so we have a data set of sales data. We can also pick this data, but once again, here we are just transferring to the driver, to the notebook, just a small sample of data. All the data is actually sitting in the executor. Next, we're going to do a very simple processing. So we are just grouping by the stock code and summing by the quantity for actually figuring out what are the top seller products. So an extremely simple analysis. As you can see, we can use Spark really as much as Pandas, like with extremely simple APIs. We can also aggregate for the country, for instance. So here we are just doing as well as the aggregation by country. But now imagine that we want to actually produce some reports where we want to aggregate both for stock code and country. So create some CSV file that we can give to country managers to help them understand better the market and plan their strategy around the sale. So this is actually a quite use case where a Spark job can be quite good. And as you can see, it's just a simple Python script where we provide an input and an output. And in this Python script, we just read the data, we process the data, And finally, we output the data. So that's an extremely simple Python script. Now, if we want to run this with Spark, we just need to upload this Python script to S3. So as you can see, we already have this Python script in the S3 buckets. And then we can just trigger this Spark job, still using the Spark client snap. So we have, as you can see, we have here the instruction where we actually say which one is the script we want to run, so the pointer to the script, as well as the input and the output. And when we actually submit this using the Spark client, now you'll see that very similarly as before, we're going to spawn some pods in Kubernetes. But now also the driver pod is going to sit in Kubernetes. So you see that now the driver pod has been spawned, and the driver pod will talk to Kubernetes to actually also spawn the executor, where the actual processing reading of data and processing will happen. So as you can see now, we also have the executor up and running, and in just a short while, then the job will be completed. And we can indeed confirm this by going to the S3 buckets and navigate to the bucket of the data. So just to make sure that, so we just need to refresh. So you see that now we have the output data. And indeed, if we download this CSV file, you'll see that we will have the result of this aggregation. So you see that we have stop code and country, and we have the quantity that has been computed. All right, so far we're only locally. So what we are going to do now is really to actually bring this Spark job at scale to Amazon EKS. But before doing that, we are actually going to enable monitoring on top of it using Juju, which is really critical. This is very critical in any production ready system where you want to actually monitor your workloads, your data. So first of all, we want to, of course, to deploy a EKS cluster. Let me just start the video. Okay. So we just want to deploy a EKS cluster. So we're going to use the EKS CTL. So basically we can provide a YAML describing our cluster. And as you can see, this is the YAML. When you actually use this EKS CTL, spawning like a new cluster, creating a new cluster takes quite some time, around 20 minutes. So I have already done this. So as you can see, indeed, like we have a EKS cluster. We can also confirm this by seeing how many contexts, how many Kubernetes contexts we have. And of course, we will have both the micro-K8s context as well as the new cluster, EKS cluster, which is this very long name. We can also confirm that indeed we are using as default the new EKS cluster. All right, that's it. So you can see that that's our current context. And the next thing that we're going to do is, of course, deploy the Spark observability stack. And this comes with, as we said, the Spark history server, which is more aiming at data scientists and data engineers, and some Grafana dashboard that is more aimed for cluster administrators. And everything will be deployed by Juju. So we're going to deploy the Charmed Spark observability stack with Juju, and then we are going to configure to use this stack using the Spark client. So first of all, we need to set up Juju. So we have to register the Kubernetes cluster. And the next thing that we have to do is to bootstrap a controller. Now, Juju controller is basically the orchestrator that takes care of deploying and managing all the other channels. So it's really like the key component of Juju that enables to orchestrate and to really operate all the application underneath. So here so you see that we are going to bootstrap this workload, this controller on K8s. Next, we need to add a namespace, a model which we call it Spark. And as you can see, now we should be ready to deploy application to using Juju. So we are going to use a bundle. So a bundle is basically a YAML which summarize all the application with all their configuration that we need to deploy. And as you can see, the Spark bundle actually is quite big. It has really several applications. And in this bundle, we also have some environmental variables that they refer to the S3 buckets, as well as the root 53 domain, because basically we are going to provide an ingress, so it's deployed on EKS. So we're going actually to use root 53 as a domain for routing all our traffic. So we are deploying this bundle. So basically we are substituting the environmental variables, and then we are deploying the bundle. And as you can see from the Juju status output, really this bundle actually has a lot of components in it, has a lot of application. The 4 that I showed before, so Traffic, Spark History Server, Grafana, and Prometheus Push Gateway, are only few, but in reality there are way more on the back end. And as you can see now, all the services they are actually going up. But by the way, I sped up a little bit this part because usually it takes a little bit longer, like a few minutes. So the last thing that we have to do to configure is actually our, for instance, Spark History Server. We have to relate it to S3 because it's from S3 that the Spark History Server will be reading all the logs. And as you can see now, like all the services are actually almost up and running. So the next thing that we are going to do is actually to expose all the services externally. So as we said, we are going to use root 53. So we have to fetch the internal address of the load balancer, the one provided by EKS. And we have to update our root 53 record. So it takes some time for the update to go through, so for the services to sync. Meanwhile, and just actually use the action in Traffic for actually fetching the endpoints. And as you can see, the endpoints that Traffic returns us already has the domain in it, and also has like the URL, for instance, of the Spark History Server. So you see that now the services are indeed in sync, and we can just navigate to the Spark History Server. In a very similar way, we can also navigate to the Grafana dashboard. So as you can see here, the Grafana dashboard supports authentication. So we can actually run an action on Juju to actually fetch the password for Grafana. So you see that with the action here, we can actually fetch the admin password. So we take the password and we copy that to the login screen. And now we're logged into Grafana. Now, if we browse to the dashboard, we see that we only have like the Grafana operator dashboard, but we can relate using the Juju Grafana with some Charm, which allows a further configuration of the bundle. So you see after the relation, basically the dashboard that they are refer in the cost configuration will be streamed to Grafana. And if now we just reload, we see that now we have a lot way more dashboard. And in particular, we also have a Spark dashboard that we are going to use in a short while. All right, now we have the observability stack up and running. The next thing that we just have to do is to configure the Spark job to actually integrate with the observability stack. Oh, by the way, here, when you have two different contexts, you also have an argument in the Spark client API that allows you to switch from one context to another. So you see that here we had the service account that we created on MicroK8s. But if we go to the default one, we don't have anything because we haven't created a Spark service account yet. So we're going to create it as much as we did before. So the user experience is exactly the same. However, in this case, we just have also to enable, as we said, the Spark jobs to be monitored. So we have to provide some extra configuration to store logs in the S3 buckets, as well as push metrics to the observability stack. So you see that here we have some configuration to allow this, where we also have some environmental variables. So what is the endpoint of the Prometheus push gateway where metrics has to be pushed. So we just export this couple of environmental variable, and now we can really add this configuration to our service account. So we can just copy this, still using the Spark client snap. so now really like the service account is really configured to integrate with the observability stack. So we are going to again submit always the same Spark job, where however now we can also increase the number of executor. So since we are in a more production ready cluster, we can also increase a little bit the resources that we can use. And as before, you see that the job has been running, and we can indeed confirm that if we go in data, and you see that now we also have another output, which is the one provided by the EKS job. And in the Spark events, we also have some extra data, and these are the logs of the application. It's basically the information that is then read by the history server to really expose these logs to user and really provide a UI to drill down on the on even the stage level of the Spark application, where the CSV was read, where it was grouped by, and so on. And also provide some information about the executor. And this is really a UI that targets data scientists and data engineers. Whereas in Grafana, as you can see, we also have metrics, and there are more metrics about resource utilization that they might be more relevant, on the other hand, for cluster administrators. So really, like providing some tools to really monitor and explore and observe actually like your Spark application. And that's it. So that's really how easy it is to set up some jobs on Spark jobs using Charmed Spark. So thank you all.
I'm pretty excited to be here on the Operator Day, actually. It's really, really, really nice to see all of those efforts. So, and I'm actually even more happy to present you why I believe that Charms really, really fit well into a product that I really, really love, which is Kubeflow, for doing MLOps on top of Kubernetes. So I think it's a really, really nice fit. And let's see why and how Charms can actually even benefit very complex projects like Kubeflow. But in order to be able to explain the full value of that Charms are going to bring, I'll need to spend quite a few minutes initially to explain what is the initial problem that Kubeflow tries to solve, which is what is MLOps. And the reason this is important is because we see more and more people asking MLOps for MLOps, but it's also crucial to realize that since MLOps is quite new, there's no uniform way across every company and standards. So that's why understanding what it is that we want to do and what are the best practices can really help here to better grasp the problem and how Charms can come into play. So what is MLOps? It's always all about predictions, having some kind of black box, which we're going to be asking you the question like, is this bank transaction suspicious? And this model is going to take a look at some data, for example, what are the last 30 transactions that this user did and their geographical location, and then respond with something like, no, it sounds pretty okay, so the transaction is accurate. And you can actually think of this black box as a live server that runs somewhere, which has its own IP and consumes resources. And there's one process inside of there that is a transformer that will take the initial data, talk to some cache to get the external data as well to be able to make the prediction, and then send all of this data, which, oh, by the way, is always a Redis cache, and then send this data to the model server to make the final prediction. And this black box of the model is always part of S3. And so this server, usually in the Kubeflow world, backed by Kaiser or Seldon, is going to first pick up the model from S3 and then load it to this server. But actually, the important part in the MLOps world is how to create a model. And to create a model, we first are going to need our data, which usually sits in a data warehouse like S3, which we can version, or MySQL for relational data. And then this data will be fit into a model, the model code with frameworks like TensorFlow and PyTorch, which this code is actually going to train our model now on top of GPUs most of the time, which take quite a lot of time and resources. And once this is done, then we have some automation code for pushing the produced artifacts into a metadata store or an artifact store. The small distinction here is that the artifact store is where we store the actual model, and metadata keeps other information about the model, like what was its accuracy, what data was it trained on, and whatsoever, so we can keep track of the best model. And usually also the metadata store points to the actual model and where it's stored. And of course, this step usually happens either in a Jupyter Notebook, which is a tool for AI and ML, or via automated pipelines. So this is the whole picture again. We have our data, we have our training step where we log our models after we finish the training, and then some model server is going to pick up this model from S3 and run it live so that we can get predictions. But this process is not just the whole picture, because we always need to make sure that the performance of the model is constantly up to the expectations. And this happens with model monitoring, which requires even more tools and stacks to be able to do it. And to be specific, we're going to need some kind of eventing system, which in the Kubeflow world, we're using Knative, which can be backed by a production service like Kafka, which then is going to ingest this data back into our initial data warehouse so that we can reuse this data later on for when training a newer model. And we're going to fetch these new predictions that our model server is getting into a detection server, usually with Sheldon Core. And if there is indeed drift, which means that the model now is not performing that much as we expected, this is where we're going to be triggering a Lambda function backed again by Knative technologies in the Kubernetes world. And these Lambda functions are going to re-trigger the whole training step so that we get a new model and then serve it with a new server. And this is how it all looks like. Plus, we need to have namespace isolation and service mesh functionalities. So this is why you will also see components like Istio being on the mix. Plus, this will need to be a whole platform on its own. So this is why we'll also have components like Dex, which can ensure that there's a single sign-on and there are users that can log into the platform. And at this point, I hope that you understand that this is why MLOps is such a complicated problem that needs to mix and match a lot of different tools and integrations. And this is also why you'll be seeing a lot of different tools and projects bundled together whenever someone needs to make an MLOps platform. And then the next problem, after we considered the actual what MLOps is we need to realize at what scale do we want to perform MLOps. And this has two scales. One is how many people are going to be involved. Is it going to be a one-man show because we have a simple model, we just build some code and then push it to a model server? Or are we having way more complicated processes where we'll need a dedicated team for handling and cleaning up the data, a team for being able to create the model and knows the specific ML logic and code to train, then a different team for being able to deploy and handle the servers into production, and of course a different team that can also have the expertise to set up all the monitoring and back to re-trigger the training. And of course, then the question becomes, how many departments of teams do we have? Is it just one team, those teams for one product, or do we have different departments with different products that need to utilize this solution? Then the next scale of part of the problem is how many resources are actually required, which translates to always, can I do something from my laptop? Is this going to run somewhere else? How much data are we going to use for this training? Is it going to be terabytes of data or a couple of gigabytes? How many CPUs and GPUs then are required to do this training, which a lot of the times will have complex training pipelines? What is going to be the result of the model size? This is especially relevant now that we're talking about those hot LLMs that are actually pretty huge. And last but not least, also questions like, what is the inference latency? How fast does my model need to be able to perform and give back a result? So with keeping all this context in mind, let's also now do a breakdown and summary of MLOps. So in order to be able to do MLOps, we need three things. One is we need the tooling. Secondly, we need the compute to be able to run the tooling and our workflows. And third, we need teams and operators that can both use the tools and operate the compute and the resource management that is going to be used. And in our case, in the Kubeflow world, we're using Kubeflow that provides us the tooling, which integrates with Kubernetes for the compute, and of course the teams that will need to operate on top of those. So at this point, let's actually take a quick look and see how the actual upstream project looks, so we can get a grasp of how things are right now. So everything starts with a manifest repo, which we can actually clone in our terminal to take a look and see live. Excuse my internet, it's not the best, but I think it will suffice for this case. So we've cloned the repo. Now let's go and take a look. Let's also check out the correct branch so that we are on the correct version. And also I'm using a kind cluster that I have installed beforehand. Upstream project also gives some instructions on how to create this one with this configuration file that is used for their testing. So with this, let's actually see what we need to do to install. So back on the repo, we have a couple of folders. I see an installation part. Okay, we have a single command that sounds interesting, or installing individual components. Let's scroll, prerequisites, a couple of tools like customize, kubectl. Okay, I've cheated a little bit and downloaded those, but let's see. So we have a while loop and a customize and kubectl. Okay, I mean, what can go wrong? Seems pretty straightforward. So let's do, okay. See a couple of warnings, but maybe that's not critical, right? I mean, they're just warnings, so, oh, nice. Okay, so everything up, oh, a lot of things apply. And are those errors? We're trying to applying resources. Oh, right, we're in a while loop, so most probably we'll just try to bluntly, okay, here are more warnings. So things should also get generated and applied again. Where do we see the warning? Okay, a lot of unchanged resources. Whoa, looks like things are getting reapplied. So is it done? Is that it? Do I have Kubeflow? Okay, things seem to be starting. So I guess that's it, right? Quite a lot of tools. Okay, so to be honest, I'm exaggerating a little bit here, but as you can see, while Upstream has given a pretty straightforward implementation of installing everything, and while a lot of the times the expectations are that this will work out of the box, the problem is exactly this. The fact that the Upstream project will give you a one-line command, but after that, everything is completely on our own to do what we need to do. And the problem here comes exactly with common day 2 operations that someone might need to do, which is like, let's integrate with other MLOps tools that someone might need. Because if you remember, as we mentioned in the beginning, there's no only one straightforward way of doing MLOps. There might be different tools that we'll need to integrate. So the ability to be able to pick and choose different tools to match our workflows, it's quite crucial. Then we might need to be able to do backups of Kubeflow databases. What if we care about our data and we want to be prepared in a disaster situation that we want to preserve our data? What if we want to upgrade into a newer version? How are we going to do it? The Upstream only gives us a command that just applies manifest on top, but how can we do an actual upgrade? And even questions like, okay, but how can I integrate with other approaches? Like, I want to do monitoring that I have. How do I integrate Kubeflow with this? Sadly, the Upstream project right now, for those, does not have a quite straightforward story yet, since the project mostly aims into developing the relations between the tools that it currently has. But here's why Charms exactly come to the rescue for such a difficult and complex platform like Kubeflow. Because with Charms, everything now is coupled around operators that will handle each of the workloads and the relations that are required between the different components. So the difference here is that instead of having upstream Kubeflow, we're using canonical Kubeflow that has charms for it, in which we have charmed all the applications of Kubeflow. So we have operator logic for handling upgrades, installation, relations, and even actions like doing backups from our databases. And all of this is powered by Juju, which also makes it easier for operators, since now they don't have to directly interact that much with Kubernetes, but via the charms and the actions that we provide, so that we simplify the management of the platform. So let's take a look actually on how this will look like to install Charmed Kubeflow. And now let's go from the upstream to our Charmed Kubeflow documentation, in which we're gonna take a look on all of the steps to get it done. So first of all, let me go and delete my previous kind cluster that we had. And as expected, no Kubernetes is running. And let's follow all of our docs one by one to see it live and what's needed to set this up. So we have a pretty beefy machine. So let's start by installing MicroK8s, Juju, Charmed Kubeflow, and Connect. So the first thing is we need a Kubernetes cluster. And in this case, we'll go with MicroK8s, which is easily provided via a snap. So you can always select what version of Kubernetes you want, and with one command, have it on your laptop or machine. Next up, though, we'll need to run a couple of small commands to make sure MicroK8s correctly configured has some permissions. So we'll just copy-paste those and put them in our terminal. I think it should be done. Yep. So let's paste the commands. Those are pretty straightforward on the kube directory, so that we can do kubectl work. Then we'll need to enable a couple of add-ons in MicroK8s, like having DNS with core DNS, host path storage for storage class, and ingress with metal-B, so we can have load balancer services. So let's just copy this command and paste it in our terminal. It should create apply a couple of add-ons, apply Kubernetes resources like deployments, cluster roles, services. So this will take a little bit of the time. We can always, let me see. Yeah, we can always check the status of MicroK8s and also use kubectl for MicroK8s to get all of the pods. So as we see, there are a couple of deployments we need to wait for to become ready. So while this happens, we can come back and take a peek at the lower levels. You can also do MicroK8 status if you want to check the status of MicroK8s and what add-ons are currently enabled and running. So we're waiting for host path storage, etc. But we can move on and go and install Juju so that we cut some time and be ready for the next steps. So there we go. We're downloading Juju. In this case, we're using 2.9 for Kubeflow 1.7, but always take a look at our docs to see the exact version we'll need for what version of Kubeflow. So this should take a little bit of the time. And then we'll be ready to bootstrap our controller on our MicroK8s cluster. Speaking of which, let's take a look at our Juju version. So we're 2.9.45. And let's see what MicroK8s is doing. So, all the deployments are ready. So most probably we can start. Let's check the status. Yeah, so all the add-ons are there. And this means we're ready now to go and bootstrap our Juju controller. So let's go. So this will create a couple of pods and namespace and a pod for the actual Juju controller. Now this can also live as a complete VM next to a cluster, and this is usually what we recommend for a production. So the two environments are isolated, but in this case, for simplicity's sake, you can just install the controller in the same cluster. So waiting for some networking. Juju needs to make sure it can reach our cluster, which should be, and there we are. So next up, we just need to add our model, which in the Kubernetes world, it's almost one-to-one with namespace. And there's also a controller in that namespace that makes sure that we'll apply all of our charms. And at this point, I'm going to apply some minor commands for iNotify in case for some systems you might bump into open file issues. And we're ready for our start command, which is deploying Kubeflow with just one command. Juju deploy the bundle Kubeflow from the 1.7 channel. Just applying this, as you'll see, is in this case, we're taking each one of the charms, applying it, and Juju will take care of also create running actions on top of this to make sure that all the charms will be applied. It should take a little bit time though, so we were going to let a little bit, and once it cooks, we should be back on with a message that the bundle was deployed. But yes, as you can see, we're installing a ton of different applications that were already part of the upstream project, but now they're charmed they have now become charms, which is Python logic for configuring and running those applications in our cluster, and so that we don't have to be the ones that will mess around with the deployments of the applications, but this is handled by Juju and the charm logic. As you can see, Kubeflow is quite a big application and has quite a lot of charms. So this is one of my main arguments of why charms can really help in such complicated scenarios where you need to mix and match a lot of different components to end up with a cohesive platform. So we have quite a lot of nice stuff going on here. Okay, it should be almost done. And we added all of the relations between the components. Relations is when we need to show that some component needs something from another. And the greatest example we can show here is that, for example, Argo over here is blocked. And the reason it's blocked is because it's waiting for object storage, which means it needs a charm that says, hey, I have object storage, and min.io says, okay, I'm waiting for you. In this case, min.io. So until min.io is up, Argo will say, hey, I cannot proceed until I get my object storage. Please give it to me. So same, we can see a lot of different components like Istio, Kubeflow pipelines, Knative, a lot of different Kubeflow components. And yeah, so this is Charmed Kubeflow. We'll have to wait a little bit for the installation to proceed. So let's wait a couple of minutes. And now that the command should have finished and everything should have run, we can take a peek at Juju. Everything should be active, and we can actually follow up with the rest of our guide. And let's see. So first one is for us to get the IP, but let me skip a little bit and first go and configure my DEX and auth service with the public URL we're going to be using. Actually, no, let me show the command. The previous command is actually going to get the public IP of our Istio, and this is where we're going to access it with the prefix that MetalB is using for us to go and reach out and connect. Now, the last step is also to configure our user. So again, via the charm, we can configure what is our username going to be and our password. And with this, we're actually ready to now reach out our cluster. Oh, we can see that because we just update the config, we need to wait for one component to become ready. So let's give it a little bit time. Let's double check also the pods are there. Yep, they are. So things should be ready to be on it. Yep, okay. So we're all set to go and try Charmed Kubeflow. The only thing we need to do is copy our URL, and here we are. Let's add credentials we set up. And we're greeted by Kubeflow's first page for creating our user that is just logged in and getting their own namespace. So as we see, this is Kubeflow, but let's also go one step further and show what was the real value of being able to use Charmed Kubeflow. And the real good value for that is that we can do also day 2 operations, and operations like that can actually be operations on top of the charms that we can actually go and configure extra and handle logic that we would need to do via the charms. And a good example for this is, for example, let's say I want to do a restore of my databases. Now, the charms that we have for the databases actually have taken care of this already and have actions that can be used for creating a backup. So secondary operations like backups are already out of the box supported. And let's go to another approach that we needed, which is integrating with other tools like MLflow. So in this case, we have our guide for installing MLflow, which we'll just follow, but skip a couple of steps initially because we're bootstrapping microkits, etc., and go right into deploying MLflow. So as you can imagine, it's also just one command for installing MLflow as well. That's similarly to Kubeflow, will apply all of the resources we needed and make the relations between the components like MLflow server and an S3 and MySQL that is needed. And as we see, our charms are also now going on, and we can go, and if we want to follow on the rest of the guide, we can also see how to continue on and fully integrate MLflow with the rest of the system. Now, those are commands we already applied, and we will just need to also deploy the resource dispatcher, apply a couple of resources, and we will be done also with integrating with Kubeflow, and Juju will have taken care of all of the little details for managing this. And yes, as you can see, we're now to say that the charms are getting up to speed, and most probably the pods right now are getting downloaded. So this will take some time. So we'll just leave this running for a little bit until everything will be fully ready. And as you can see, all of the pods are running and are owned by our charms. Let's also take another quick look and describe what is going on. I think, yes, so we're pulling the images and we'll have to wait a little bit for MLflow to fully download. Let's see. Okay. For the interest of time, though, we will skip to the next part, which is going to be to recap on what are the benefits of Charmed Kubeflow. And those benefits, as you saw, is that now the charms encapsulate all of the operator logic that we would need to be able to run our ML platform into self-hosted units of code, which is Python, that control those upstream applications. Charms can act as building blocks, as we saw with MLflow, that we can use and interact and as pluggable components into our own platform. And also we can have actions to the workloads, like the powerful actions we saw for taking backups, which are pretty useful actions and things that are actually the day 2 operations that everyone will need once they start using Kubeflow.